Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everybody. How's everyone doing on this evening in week 4? Wednesday of week 4. Really good. It's good. That's good. I'm feeling great. So it's for those of you guys who follow NBA know that we're kind of right in the middle of the playoffs, and yesterday there were 2 really fantastic games. So one for the Eastern Conference, but more importantly, there's a Game 7 between the Nuggets and the Clippers, and the Clippers lost. And as a lifelong Lakers fan, nothing makes me happier than that, especially this year when the Clippers and their fans were talking crap all year. So to see them exit like that was very, very satisfying for me. Okay. So the plan for today is we're going to finish up our lecture notes on truss elements. So we just have a couple more pages to go. So we have one more example and just one more thing to do. And then after that, we're going to jump into our next set of lecture notes, which is on beam elements. So we'll see how those are going to be. But what you'll see is that our same process is still going to apply. It's just that for beam elements, we're going to consider different modes of deformation. Okay? So before we get started today, are there any questions just on the homework or anything that we covered in the lecture last week that I can answer before we get started? Okay, so let's go ahead and get rolling. Okay, so the last thing that we covered on Monday was, the fact that, when we're doing these structural finite element problems with the stiffness method, we can have different kinds of supports. And so the one that we've been using up until this point has been known as, we'll call it the pin support. And so a pin support will basically prevent deformation in any, or prevent displacement in any direction. But last week, or last time in class, we introduced the roller support, which will only knock out the displacements in one direction. So let's kind of see it in action in the example, okay? Okay, so for this example, we have a 2-element system. Okay. So our 2-element system is going to have 2 supports. So we're going to have one element that goes this way, right? And so this is going to be element A, right? And then we're also going to have an element that goes horizontally like this. Okay, and this will be element B. And so let's label our nodes. So we'll call this node over here node number 1. We'll call this node number 2. And we'll call this node number 3 right here. Okay. And so let's put some dimensions on this guy. So this will be 5 feet right here. And this will be 10 feet. Okay. And so we also need to define the material properties for this for these truss elements. So first we have the Young's modulus. Young's modulus will be 30 times 10 to the 6th psi. And we also have the area. And so the area is going to be 1 inch squared. Okay. And so both of these elements are going to share the same Young's modulus and cross-sectional area. Okay. And so just like we did in the previous example, what we're going to solve for are the nodal displacements. And then we're also going to solve for the stresses in each element. Okay. Oh, I forgot the most important thing. So we also have a mode, vertical mode here on node 1. And this vertical mode has a magnitude of 25,000 pounds. Okay. So I did in red just to make it stand out. Okay. And so this is a pretty standard, 2D truss problem. So we just basically have 2 elements and 3 nodes, right? So where this is different from the last one is this guy right here. Okay? So instead of a pin support, which is going to knock out both of the directions of the displacement, we have a roller support, which is only going to prevent displacements in one direction. Okay? And so normally, if we consider the pin support up here, right? And so for the pin support, right? So pin support will knock out the displacements in both directions. So in this case, we have a pin support at location 2 or node 2, And so what this means is that we're going to have u2x is equal to u2y is equal to 0. Okay. And so basically both components of the displacement are going to be 0 because that's what the pin prevents. Okay. But for the roller support, remember the roller support only knocks out the displacement in the direction that's perpendicular to the support. Okay. And so in this case, the direction perpendicular to the support is in the x direction. And so all we can say is that u3x is equal to 0. Okay. But since we only have a roller support at node 3, that means the y direction of the displacement at node 3 is going to be free. So u3y, we're not going to put any constraints on that. So it's still going to be part of our global stiffness matrix, and it's still going to be something that we can solve for. Okay. All right. Any questions on the problem setup? Okay. All right. So let's go about and solve this in the same way that we did before. So first, we're going to start with the element stiffness matrices. Okay, so let's start with element A. Okay. And so the main thing that we need to know when we're doing element stiffness matrices for truss elements is we need to know the angle that it makes with the positive x-axis. Okay. And so I don't think we've done one like this yet, but the way that I like to do these is I like to see how the element has rotated from the positive x-axis. Okay. And so even though our element looks like this, right? Oh, we need the angle here. Forgot to put that in the figure. So this angle right here is 30 degrees. Right? So that's the angle that it makes with the other element. Right? So even though our element A looks like this, right? We have node 1 and node 2, right? And we know that this angle right here is 30 degrees. Okay. If we actually compare the angle with the positive x-axis, so the positive x-axis is like this. I'll actually draw in a different color. Right? So if we draw the positive x-axis like that, then our angle is actually going to be this guy right here. Okay, so this is actually going to be 150 degrees. Okay, and so there's lots of different ways that you can do these problems, and I've actually seen some people in office hours do these a little bit differently. But the way that I like to do it is I kind of like to think of the elements where the pivot is at the lower node number. Okay. Okay. So in this case, the lower node number is 1. And so if we pivot around there, how much do we have to rotate in order to get the element orientation? So in this case, the amount that we rotated was 150 degrees. So for this problem, or the way that I'm going to characterize this element stiffness matrix, is with the angle of 150 degrees. Okay? And so when we plug in for like cosine of the angle and sine of the angle, we're going to do it with 150 degrees. So let's go ahead and do that. Right? So we have cosine of 150. Okay. And so this is going to be minus root 3 over 2. Okay. And then we have sine of 150. It's going to be a positive 1/2. Okay. Right. And then so now that we know the angle and we know all the material properties for that element, we can go ahead and fill in the element stiffness matrix for element A. Okay. So we have 2.5 times 10 to the 5th. Okay. And then we're going to multiply by our, all our terms with the sines and cosines. So we plug in everything, we're going to get 3/4, and then minus root 3 over 4. Right? Minus 3/4. And then root 3 over 4. Right? minus root 3 over 4, 1/4, root 3 over 4, minus 1/4, right? Minus 3 over 4, root 3 over 4, 3/4, minus root 3 over 4, root 3 over 4, minus 1/4, minus root 3 over 4, and then 1/4. Okay. So it's a little bit, tedious just because we have an angle that's not 0 or is not 90. But this is, if you kind of compute all the sines and cosine terms, this is what you get for this guy. Okay. All right. Any questions on this, especially on the angle thing? So I know the angle thing can be a little bit confusing kind of the first time that you see it. Yeah, sure. So, these numbers, remember, this was based on the element stiffness matrix that we had before. So a lot of these numbers, like I know this guy right here is like cosine squared, right? And so you would take whatever you got for cosine of the angle, and then you would just square it. And so minus root 3 over 2 squared would be 3/4. And then this guy right here is, I think, a cosine times a sine, right? So this is CS right here. And so to get that number, you would take minus root 3 over 2 multiplied by 1/2. Yep. Yeah, and then you kind of just go from there. So it's a lot of sines and cosine terms, but then if you go back in the notes and then the expressions there, and you just kind of plug stuff into that. All right. Any more questions on this? Okay. So that's element A. So then now let's do element B. Okay. And so element B looks something like this. Okay. And so it's a horizontal bar. So I think the tempting thing here is to say that the angle for this guy is 0. But since the lower number node is on the right here, we can say that the positive x-axis is like this. Okay. And so if the positive x-axis is like that, then the angle is actually going to be 180 degrees. Okay. All right, so cosine of 180 is going to be minus 1. And then we have sine of 180, which is going to be 0. Okay. All right, so then once we fill these into the element stiffness matrix, it's going to look like this, right? It's nice when our elements are either 0, 180, 90, 270. So because we have the 0 right here, a lot of things are going to cancel out. Right? So this is going to be, let me make this a little bit more clear. Right, so this is going to be 5. E5. Okay. So element B has half the length, so that's why we have a bigger number out front. Right? And then we have 1, 0, minus 1, 0, 0, 0, 0, 0. Okay. Minus 1, 0, 1, 0, 0, 0, 0, 0. Okay. And this is acting on U1x, U1y, U3x, U3y. Yep. Okay. So those are our two element stiffness matrices. And then now the next step is just to simply assemble, apply boundary conditions, and then solve. So, same process that we've been doing. Right? Any questions on the element stiffness matrix for element B? Okay, so let's go ahead and finish up this problem. So with the assembly, right? And so after assembling all the different element stiffness matrices, we end up with the following. Okay, and so since we have 3 nodes in our system, we're going to end up with a 6 by 6. because we for each node we're going to have both an x and a y displacement, right? So we're going to have 10 to the 5th out in front. We're going to have 6.875 minus 1.08 minus 1.875, 1.08 minus 5, and then 0. Okay. Minus 1.08, 0.625, 1.08 minus 0.625, 0, 0, minus 1.875. I'm totally going to run out of room. 1.08, 1.875, minus 1.08, okay, 0, 0, 1.08, minus 0.625, minus 1.08, 0.625, 0, 0. Okay. Then we have, we're going to continue on to the next line. And so we have minus 5, 0, 0, 0, 5, 0, and then a column of all zeros. Okay. And this is multiplied by u1x, u1y, u2x, u2y, u3x, u3y. Okay. And so those are our, that's our global element stiffness, or global stiffness matrix before we apply the boundary conditions. Okay. Okay. And so at this point, you know, our next step is to apply the boundary conditions. And so we know that from the boundary conditions that these three guys are going to be equal to 0, right? Because we had a pin support at node number 2. And so pin support at node number 2 means that u2x is going to be equal to 0, and also u2y is going to be equal to 0. And we also had a roller support on node number 3. And so that roller support was kind of vertical like this. So what that means is that u3x is going to be equal to 0. And so we're going to apply the boundary conditions where we replace the row with the appropriate 1 in the column, and then we put 0 on the right-hand side. Okay. And so before I do that, I want to bring you guys' attention to something here. That some of you might have encountered this already in the homeworks, but what you'll notice here is that we have a column of all zeros, and we have a row of all zeros. Okay. And so this is pretty significant. So even after you apply your boundary conditions, your Drishlay and your Neumann boundary conditions, if you have a situation where your global system has an entire column of zeros and a row of all zeros, you actually won't be able to invert the matrix. All right. And so if you ever come across a situation where you have an entire column of zeros and an entire row of zeros, most of the time they're going to be matched. So you can see in this case we have the last column and the last row, right? So those, if you kind of look at those rows, you should see that those correspond to u3y, right? And so if you ever get a situation like this, before you actually plug it into MATLAB and you try to solve it, what you need to do is you need to eliminate these from the system. So what we're going to do is we're basically going to delete that entire row and delete that entire column, okay? And so now what we'll have is just a 5x5 system of, for the displacements, okay? And so, the reason we do this is because, numerically or just from linear algebra, if you have an entire row and column of zeros, then there's no way for you to actually find out the value of that parameter. So basically what we're saying is that u3y just doesn't show up in our linear system of equations at all. Because remember, this system right here represents, supposedly 6 equations and 6 unknowns, but, because we have a row and column of all zeros, all we have is basically just a system of 5 equations and 5 unknowns. So it doesn't make sense to try to solve for a variable that doesn't even exist in our system. And so we're just going to eliminate it. So after doing this elimination, what you should end up with is instead of a 6 by 6, you'll have a 5 by 5 system. Okay. All right, so does that make sense as to why we eliminate that row and that column? Yeah, so I'll do that on the next page. So in order to apply the Drishlay boundary conditions, we're gonna replace these 3 rows with the 0, 0, 1, 0, 0, 0, 0, 0. Yeah. Yeah, so we have 3 Drishlay boundary conditions here. So we're gonna replace those 3 rows. Oh, that reminds me, Eric. So the typo that we talked about last time, there was a typo in the solution. So I uploaded an updated version of the homework assignment that has the correct solution for that problem. Okay, so let's go ahead and finish up this problem. So next step is to apply our Drishlay and Neumann boundary conditions, right? And so now we have a 5 by 5 system, so it's a little bit easier. Hopefully I can fit it all in one line this time. Okay, so we have 10 to the 5th, right? And so going across the first row, we have 6.875 minus 1.08 minus 1.875 minus 5, and then I missed one. Minus 1. Oh, this should be 1.08 and then minus 5. Okay. All right, and so our next row is minus 1.08, 0.625, 1.08, minus 0.625, and 0. Okay. And so remember those rows have to do with U1x and U1y, and so those are degrees of freedom that we don't have any restraints on. Okay. But for all the other ones, we do have some restraints, so we need to do the row replacement. Okay. And so for U2x, that's going to be like this, right? So we have 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 0, 1. Okay. And so remember, when you were doing the replacement for the Dirichlet boundary conditions, you replace the diagonal, you replace it with an entire row of zeros, then you put 1 on the diagonal position. Okay. And so this is going to be multiplied by U1x, U1y, U2x, U2y, and then U3x. Okay. And so remember, we've eliminated U3y from the system because there was an entire row and column of all zeros. Okay. Right. And then from here, we can apply our Neumann boundary condition. And so our Neumann boundary condition, remember, was a load of minus 25,000 pounds. And that was applied in the y direction on node number 1. So this can be minus 25,000. Okay. And 0, 0, 0. Okay. Okay, so then now that we have the system in this form, we can just solve it in MATLAB. Okay. All right, so there's a question in the chat. So I put 1 at the intersection of zeros, and I got the correct result without deleting any rows and columns. So in this particular case, that works. And so what you're basically saying is that U3y is going to be equal to 0. So you're basically applying another Dirichlet boundary condition on U3y. So this is kind of a simple example, so it would work. But I want you guys to get into the habit of eliminating that rows and columns from the system, because for more complicated situations, it might not work exactly like that. Because it might be something that's, basically what we're saying is that we're not able to solve for that displacement based on this. But right now we're still in relatively simple conditions because we're doing trusses, where trusses can only display or displace axially. But once we start adding beams and rotations and frames, then then, you know, I want you to kind of do it this way, just so, you know, you kind of capture everything correctly. Okay. And so any questions on the global system here? Okay, so let's go ahead and finish this up. And so if you solve the for this solution, you get the following. All right, so you get u1x is equal to minus 0.0862 inches, and u1y is equal to minus 0.549 inches. Okay, and since all the other guys are on the Drishlay boundary condition, we can just say that they're all equal to 0. Okay, and there's our solution. Okay. And then from this solution, you can compute the stresses, right? And so remember, the stresses are given by this expression. So let's say we want to compute the stress in element A. And so that's going to be E over L, and then we have minus cosine, minus sine, cosine, sine. Okay. And then we need to multiply this by the displacements of that element. So for this displacement, so the element A is bordering nodes 1 and 2, right? So we're going to multiply this by u1x, u1y, u2x, u2y. Okay. And so we know here that the angle is 150. Okay. And so if we plug everything in, we get sigma A is equal to 49,962 psi. Okay. And then we can do the same thing for sigma B. So sigma B is going to be the same thing. Okay, so we have E over L times minus cosine, minus sine, cosine, sine. Okay. But sigma B is bordering nodes 1 and 3. So we're going to do U1x, U1y, U3x, U3y. Okay. And we get sigma B is equal to minus 43,100 psi. Okay. Right? And so once you have your displacement solution, it's a simple matter to compute the stresses. You just kind of plug it into this formula that we have right here. Okay. All right. Any final questions on this example here? Okay. All right. And so the last thing that I want to go over in this lecture notes for trusses is this concept of symmetry. So I'm going to introduce symmetry within the context of just kind of truss problems and beam problems, but symmetry is actually a really powerful tool that you can use for really practical FEA as well. And so, you know, the whole idea with symmetry is that if you have a structure that kind of, you know, looks the same on both sides, you know, you can basically put a mirror in the middle and it looks the same. What you can do from a finite element perspective is say, you know, if you have the exact same structure on both sides of this mirror or the line of symmetry, you know, why don't we only just do the analysis on half and then kind of just mirror the results on the other side? So we're basically solving a problem that's only half as big as before, which for some cases, you know, is a really, really big deal. And cutting your cost in half is usually huge. Okay. And so just to kind of illustrate what symmetry is, let me give the following example, right? Okay. And so say we had a structure that looks like this. Okay, so it's a 4-element system. So let's say we have element A, element B, element C, element D, right? And we have nodes 1, 2, 3, 4, and 5. Okay. And so we have 4 elements and 5 nodes. So this is, you know, a relatively complex structure. Okay. Multiply for the area because it's 1. Yeah, so in the previous one, you know, I already kind of computed that EA over L. So that's where the area came in, was for that constant out in front of the stiffness matrix. Okay. And so, you know, let's say that we have a load right here. Okay, so we'll call the load P. And let's say that we wanted to find the finite element solution to this system. Okay? And so, you know, this system right here is not the worst thing in the world. But if we compare that to the system that we had on the previous example, this is basically twice the amount of work, right? So we have twice the amount of elements, and we have 2 more nodes. So we're going to end up with a 10 by 10 system that's going to be kind of a little bit nasty to solve. Right? And so one thing that we can do is we can say, okay, you know, we have this structure, but if we kind of like drew a line kind of halfway through the structure like this, right? And we kind of look at across the line, and we basically see that there's basically a mirror image on both sides, right? Okay. And so in these situations, you actually don't need to solve the entire system. So actually what you can do is you can just solve just half of this and then just assume that the same thing is going to apply on the other side. Okay? And so what you can do instead is you can just solve basically the problem that we had before, right? We have something that looks like this, right? So this is only half the structure. But there's one important thing that you need to do when you apply symmetry. So whenever you perform a symmetry cut, and so you basically cut the structure in half or in quarters or however many times you want to do it, in order to basically preserve the effects of the other side, what you need to do is you need to place a special boundary condition where you made the cut. Okay. So use green for this. Okay. And so that special boundary condition is to place a roller basically right where you made the cut. Okay. Okay. And so symmetry is a really powerful tool, whereas like you can cut the amount of work that you have to do in half, but you have to make sure that you apply this roller constraint just so that it's going to you know, be you're going to get the correct solution. Okay. And so the reason for that is because, you know, even though we're only solving half the structure, you know, there's still another half of the structure that's over there. And so what you're saying basically is that this roller is preventing displacements in this direction. Okay. And so the reason you can't have deformations in that direction is because in reality, there's a whole other part of the structure over there. So it doesn't make sense for you to basically cross that line and invade on that territory, because, you know, the structure over there will stop it. Okay. Yeah. So the question is, yeah, the orientation of the roller is parallel to the cut. Mm-hmm. All right. So the other question is, what's the word before constraint? Roller constraint. Clear. So it's a special constraint that basically only constrains the displacements in one direction, but lets it be free in the other ones. Okay. Any questions on symmetry? Okay. And so I want to give you just a couple warning things for symmetry. And so symmetry can be, you know, really tempting, especially if you. Oh, is there a question? If we have a spring instead of a beam and beam 5, yeah. So I'm going to cover that just now, actually. And so, you know, symmetry can be really tempting to use if you have kind of similar things. but it really needs to be perfectly identical on both sides. So the situation that Uriel is talking about right now is say that we have our structure that looks like this, right? So we have trusses on both sides right here, right? But instead of a truss element over here, let's say we have a truss element right here, let's say that we have a spring. So in this situation, even though the geometry itself is symmetric, and so, you know, if we kind of ignore the fact that this is a spring right here, you know, we have a perfectly symmetric structure, right? But in this case, we cannot apply symmetry. Okay. Because even though the geometry is symmetric, the elements on both sides are not symmetric. And the reason for that is because, you know, we have a spring on one side and truss elements on the other one. And so, you know, all the elements basically have to be perfectly identical. Okay. Okay. And so that's one thing. Yes. Yeah, so if you do want to apply symmetry on this, there would have to be a spring on the left-hand side as well. Yeah. Right, so the question is, so the stiffness matrix and E and A must also be the same on both sides. Yeah, so so all the properties and everything have to be the same too. All right, so the question is, but then it can move in the X direction too. Can we use the roller? So, you know, it can move in the X direction, you know, if we have this spring here, but because of the loading, you know, it's only going to displace in the Y direction. So in that case, you know, even if we have springs over here, you would still do a roller type. And so if you cut this by symmetry, right? So say if we had a spring on both sides, it would look like this. And so we would still put the roller in order to prevent that displacement in that direction. So it can still displace vertically, but not horizontally. Okay. Yeah, so in symmetry, it doesn't matter if you're using a spring or a truss, or even with beams and everything. So the only condition is that it has to look exactly the same on both sides. So element types, element properties, and we'll go over one more thing, which is boundary conditions also have to be symmetric. You know, you can, as long as all those are the same across the symmetry line, you make the cut and you put a roller condition right there, and that's how you analyze it with symmetry. Okay. Yep. Okay, so then let's also talk about boundary conditions, because the boundary conditions are also really important too. And so you can't apply symmetry if the boundary conditions are also not symmetric. Okay? And so let's take the same situation. Okay. And so let's say that, you know, instead of a force that's going straight down, let's say that we have a force that's going like this. Okay? And so it's skewed to one side. Right? And so in this particular situation, you cannot apply symmetry because the boundary condition is not symmetric across that. So if you drew your line like this, right? Then the left side of the structure will have a force that's going to the left, but that's not present on the right. So you know what, you need to make sure the boundary conditions are the same. Okay, and that also has to do with the constraints too. So if on the right hand side we basically have fixed constraints, on the left hand side we have fixed, right? But on the left hand side we have a roller instead. So let's say that we have a roller right here. And so, you know, in this situation, even if the element types, even if the element properties are all symmetric, because our constraints are different on the left and the right side, we can't apply symmetry in this case. So you have to be really careful just to make sure that, you know, everything, every single detail is exactly the same across their symmetry lines. So element types, element properties, constraint types, boundary conditions, loads, everything has to be the same. Okay? And so it seems really constraining, but this actually happens quite a lot in engineering situations, because engineering, oftentimes we make structures to be quite symmetric with each other. So there's a lot that you can do with symmetry. Okay? Right, so the question is, this translates to fewer compute cycles during simulation because the matrix is smaller. That's absolutely right. So that's the main motivation of why you want to do symmetry. So, for a practical problem that you're running in ANSYS, if you are only analyzing half your structure, that means you're going to have half your elements and almost half your nodes, and then that means your compute time is going to be that much faster. Yeah. So it's all about cost saving, right? So if there's clever things like this that you can do to reduce the cost of your simulation or your finite element analysis, then you should absolutely do it, because it's time and computation time is kind of the big limiting factors for finite elements. Okay. All right, any final questions on symmetry? Okay. So that brings us to the end of the truss notes. And so our next unit is going to be on beam elements. So we're going to introduce a whole new element type. But what you'll see is that, even though it's a whole new element with a whole new, types of deformation, our process is still going to be the same. Okay. Okay, so let's start, with kind of just reviewing just a little bit about springs and trusses. Okay. So in the problems, probably, if you've looked at the homework already, you'll see that springs and truss elements can, truss element, another word for them is bars, they can kind of be used interchangeably between each other and not really change the results. And the reason for that is these guys are limited to only axial displacements. Okay. And so the key word here is axial, right? And so whether you have a truss or a spring, right? And so if we consider basically the local system of the elements, the displacements always just go this way, right? So we have U1 and U2, okay? And so there was no way, or this was kind of one of our assumptions when we were doing our truss elements, was that you cannot have any displacements like this, and you cannot have any rotations. Oh, I haven't uploaded the beam notes yet? I thought I did. It should be on week 4 of the Canvas site. So it should be right under the truss equation notes, and so there should be an upload for beam equation notes as well. Although I hope it's the right file. Let me see. Yeah, it should be up on the Canvas site. So it's looking week 4 of the Canvas site. Yeah. Okay. Okay. And so even though truss elements and springs, this is kind of a good place to start. We're really limited in the kinds of structures that we can analyze, because in reality, these structural elements can also exhibit, or let me color code this a little bit better. And so we'll circle those in red, and we'll circle these in blue. Okay. And so in red, red is what I've circled there are displacements that are perpendicular to the length of the element. And so in red, we have basically transverse, we call those transverse displacements. Okay. And then in blue, what we have are rotations. And so real life structural elements can have these transverse displacements and these rotations. And so basically what we need to do is we need to have a new element type to basically accommodate these different deformations, okay? And the element type that we're going to use is a beam. Okay. Okay. And so a beam looks, just like that. And so it looks just like this. But instead of having displacements in the axial direction, what we have instead are displacements in the transverse direction. So we'll call this U1y, and we'll call this U2y. Okay. And then we'll call the rotations theta1 and theta2. Okay. And so in order to and so what we're going to do basically is we're going to take this beam element, start with the Euler-Bernoulli beam equation actually, and then we're going to take this and derive the element stiffness matrix so that we can actually perform finite element computations with beam elements. All right, any questions on this? Okay. So right off the bat, you know, what you should notice about the beam is that we have 4 degrees of freedom instead of 2, right? So for the bar, we just had the axial displacement on the left side and the axial displacement on the right. But for the beam, we actually have both a transverse displacement and a rotation on both. And so our element stiffness matrix is actually going to be 4 by 4. Okay? And so if we actually draw it out, it's actually going to look like this, right? And so remember, the purpose of the element stiffness matrix is to relate the nodal forces, and in this case also the nodal moments, and we're going to relate that to the nodal deformations or nodal displacements. Okay? And so for the forces, we have Fy1, which is the force on node 1 in the y direction. Okay? M1, so M here represents a moment. Okay? And the same thing for node 2. And so we're going to have Fy1, M1, Fy2, M2, right? And so here's going to be our element stiffness matrix, okay? So call this K beam, right? And then on the right-hand side here, we have, or on the right of this expression here, we have the corresponding nodal deformation. So we have Uy1, theta1, Uy2, theta2, okay? And so the question is, how do we get this guy here? Okay. And so our starting point is going to be the beam equation, right? So you might have seen this in a previous structural mechanics class. But our beam equation looks like this. Okay, so we have the double derivative with respect to x times E, which is still going to be our Young's modulus, multiplied by I. So I, remember, is the moment of inertia of the cross section of the beam. And that's going to be multiplied by the second derivative of the transverse displacement. Okay? And this is equal to minus W of x, where W of x here is a distributed load. Okay? So this is basically just a straight up Euler-Bernoulli beam equation that you might find in your text, in your previous textbooks. Okay. And so this form of the equation, it's a little bit, it's kind of a lot to use. And so we're going to make some assumptions. And so the first assumption that we're going to make is that we're going to have no distributed load. And so the right side of this is going to be equal to 0. Right? And then the second assumption that we're going to make is that E and I, these guys are going to be constants. Okay? As we have constant material and geometric properties. Okay, and so if those two guys are constants, we can bring them outside the derivative, and so we're going to get a much simpler expression. Okay. All right. Any questions on this? Yeah. So yes. So Chris is making a comment on something that we're going to see after the midterm, which is the concept of weighting functions. So that's looking ahead a little bit, but yeah, this W of x right here is actually a distributed mode. So we'll deal with weighting functions after the midterm. Okay, and so if we apply those assumptions, that simplifies our equation quite a bit. Okay, And so now what we have is E times I times d to the fourth uy times d or over dx to the fourth, and all this is equal to 0. Okay. Right. And so at this point, we're going to make an additional assumption. So we're going to assume that our rotations are going to be small. And so we're not going to do anything crazy like, have a beam that's like a shape in the U, right? And so in the limit of small rotations, we can express the rotations actually in terms of the transverse displacements, right? And so in the limit of small rotations, what we can assume is that theta I, which is the rotation at node I, is equal to d u y I dx. And so our rotations are nothing more than just the derivative of the transverse displacement with respect to x. Okay. And so these are basically going to be our governing equations for the beam. And so I'm not going to run through the entire full length derivation because that's kind of a lecture in itself. But I will just kind of give you kind of the highlights and kind of the big kind of picture ideas. Okay? And so kind of the biggest picture idea kind of brings us back to, just the interpretation of what the stiffness matrix actually represents. Okay. Remember, the stiffness matrix represents the relationship in between the nodal loads, and so the forces and the moments, and the corresponding displacements. Okay. And so from these governing equations, what we want is we want to manipulate them in such a way that we get a force equal to some displacement. Okay? And so we want the relationship between loads and deformations. Okay. And so if we manipulate these equations and we kind of bring in some other equations from elementary beam theory, what we get is the following expressions. Okay? And so from beam theory, so I want to skip I want to skip a lot of these steps for now, just because of, I want to do an example before we do the lecture today. But actually, at the end of the beam lecture notes, I'm going to bring it back a little bit and talk about, how did we get these equations to begin with. Right? And so from beam theory, we have the following expression. So we have m of x, where m, again, represents a moment. Okay. Another word for moment is like torque. So moments and torques are, the same thing. Right, so it's going to be EI times d squared uy dx squared. Okay. And so here, this is basically the relationship that we want, where we have on the left-hand side here, we have one of the loads. And so one of the loads for a beam is a moment or a torque. And then we have the relationship between that and the displacement. So given it's a derivative relationship, but it's a relationship, which we can have. Okay? And so the other relationship that we have is between the nodal forces. Okay? So it looks very similar. So we have EI times the third derivative of the transverse displacements. Okay? So we have EI times d cubed dy, d cubed u sub y over dx cubed. Okay. And so now that we have these kind of force displacement relationships, we need to turn these into linear equations. Okay. Okay. And so again, I'm going to be skipping a lot of these steps for now. We'll come back to it later when it's kind of more relevant. But I kind of want to just focus on this discussion on, let's get our element stiffness matrix. let's do a practice problem just so you can kind of see it in action. Okay. All right. Any questions on this? Okay. Okay, and so after we go through that derivation, which we'll come back to it, I promise. I'm not going to cheap you guys out of something like that. And so we get the following system. Okay? And so first, let's start with our element stiffness matrix. And so our element stiffness matrix looks like this. So we have E times I all over L cubed. So that's the constant out in front. Right? And so remember here we have a 4x4 system. Okay? And so we have 12. 6L minus 12 and 6L, right? 6L 4L squared minus 6L 2L squared minus 12 minus 6L 12 minus 6L 6L 12L, sorry, 2L squared minus 6L and 4L squared. Okay. And so this is going to be multiplied by our displacements. So our displacements are going to be UY1, or U1Y, sorry. Get those reversed sometimes. Theta 1, U2Y, and theta 2. Okay. And all these are going to be equal to the nodal load. So we have F1Y, M1, F2Y, and M2. Okay. And so this guy right here, which I'm going to box in red, this right here is our element stiffness matrix, or B. Okay. And since we just got done talking about 2D truss problems, it's important to note that this is the element stiffness matrix in the local coordinates. Okay. So we haven't done any transformation matrix to bring this into the stationary coordinates. That's actually going to be once we do frame equations. But for now, this is just the local element stiffness matrix in the local coordinates. Okay. And so I know, I skipped a lot of steps in this derivation, but ultimately, this is the element stiffness matrix that you can use for beam problems. So, you can use this element stiffness matrix in the exact same methods that we did before. Okay. And so actually, before we do an example, I want to talk about constraints a little bit more, but I think I'm going to need a whole slide to do that. But are there any questions on this slide right here? Okay. And so let's talk about constraints. And so we're going to add one more constraint. So far, we've seen pin constraints, we've seen rollers, but there's actually one more that we can do. Okay. And the reason, we have to introduce another constraint is we have an all new degree of freedom that we're considering in here, rotation, right? And so right now, actually, the pin support, both the pin and the roller support, they're not able to constrain rotation because, a pin, you can think of it as something that you kind of stick a pin into where it might prevent the thing from translating, but, it can still rotate. And so we need a new type of support that can actually remove the rotation. And the way that we're going to call it is called a fixed support. Okay. And so the way that fixed supports are usually denoted is that the element itself looks like it's just coming out of the wall, just like that. Okay. And so in these cases, you can basically think of it as like the element is kind of super glued or like cemented or like built into the wall, where at this location right here, you're not able to have any kind of displacements or translations, and you're also not able to have any rotations too. So the fixed support is kind of the strongest support that you can have. And so in these cases, u sub x is equal to 0, u sub y also equal to 0, but then also the rotation is going to be equal to 0. Okay, and so that's the first type of constraint. Okay, and that's actually the new one. And so let's talk about the other ones. Okay. And so the next type of constraint is a pin, right? So it might look something like this. So you have your element, and it might be pinned like this. Okay. So usually a pin is denoted by triangles like that, right? Where the triangle is kind of fixed into the wall. And so in these pin cases, we've seen these before. These pins will prevent any kind of translation. So both ux is equal to 0 and uy is equal to 0. Okay. But the pin's not going to be able to constrain any rotation. So the rotation that you get at a pin is something that you still have to solve. Okay. Right, and our last type of constraint is a roller. And so the roller is denoted by a triangle on wheels. And so we've seen the roller already. So the roller basically will prevent deformation in normal to the roller, but parallel to the roller, you're still able to find deformation. So in this case, if we consider the x-axis this way and the y-axis that way, ux will be free, uy will be constrained, and then theta will also be free. Okay. And so, when you're doing beam problems, it's important to know these constraints, especially with regards to the rotation. So you need to know whether you're going to constrain the rotation or you're not. So the question is, are we going to do joint constraint types, or is that beyond the scope here? So for these kinds of problems, these are the constraints that we're going to be fixed to. But as we explore ANSYS more and as we kind of get into the after midterm stuff, then the constraints will be, this kind of intuition will help us, but it's going to expand into different types of constraints. But we'll kind of cross that bridge when we get there. Okay. All right, any more questions on this before we jump into an example? I think we have time just to do one more example before we close for today. Okay, and so let's do an example with a beam. Okay, and so let's consider a case where we have a 2-element beam that looks like this. Okay. And so let's say this is our element A. Okay. And our element B looks like this. Okay. And so just from the figure up here, we can see that our beam is going to be fixed at element A, or at the left side of element A, right? And then on the right side here, we're going to have a pin support. Okay. And so we have 3 nodes in our system. Okay. So we'll call this node number 1, we'll call this node number 2, we'll call this node number 3. Right? And so both of these beams will have the same length. So we'll say that they have a length L. And then let's talk about the load. So let's say that we have a force going downwards, like this. Okay. And so we have a force like that. And then we also have a moment that we're going to apply. And it's going to be counterclockwise, just like that. Okay. Right. And so this problem we're going to do just with the symbols, just so you can kind of see, and I think, we've gone through the process of element stiffness matrix assembly boundary conditions several times. And so we're going to assume EI, which is the product of the properties. This is going to be constant through the beam. Okay. And we're also going to ignore any axial displacements. Okay. And so we're not going to be dealing with trusses here, so these are all just pure beams. So we're only going to have transverse displacements and rotations. Okay. All right. Any questions on this before we go about solving it? Okay. Okay, so just like we always do with these kinds of problems, hopefully it's becoming second nature to you guys. So the first thing that we're going to do is the element stiffness matrix for each of the elements. Okay. And so in this particular case, the element stiffness matrices themselves will look the same, but remember, it's important to keep in mind which nodes that these elements are acting on. Okay? So let's do Ka first. Okay? So Ka will be Ei over L cubed. Okay? And that's multiplied by 12, 6L, minus 12, 6L, 6L, 4L squared, minus 6L, 2L squared, minus 12, minus 6L, 12, minus 6L, 6L, 2L squared, minus 6L, and 4L squared. Okay. And so we also need to know what nodes that these guys are acting on. So element A, in this case, is acting on nodes 1 and 2. And so we have U1y, theta 1, and U2y, theta 2. Okay. All right, so that's element A. And so element B will be the same thing. So, we assume that all the properties are the same. So I'm not going to rewrite it again. But the nodes that they act on are different. So we're going to have U2y, theta 2, and then U3y, and theta 3. And the reason for that is that element B is acting on nodes 2 and 3. Okay. Okay. And so now that we have this element stiffness, we can go ahead and assemble, right? Okay. And so our global system in this case is, since we have three nodes and 2 degrees of freedom per node, and so our global system will be 6 by 6. Okay. And so I'm definitely going to have to do that on the next page. So are there any questions on just writing out these element stiffness matrices here? Okay. Okay, so let's write out the global system. So our global system is going to be 6 by 6, right? So we can't forget our constant out in front. It's easy to forget him, right? But let's not forget him in this case. Okay. And then let's write out our 6 by 6 system. Okay? So we're going to have first the contributions from element A. So we're going to have 12, 6L, minus 12, 6L, 6L, 4L squared, minus 6L, 2L squared, minus 12, minus 6L, 12, minus 6L, 6L, 2L squared, minus 6L, and 4L squared. So don't feel pressure to write all this down in your notes right now, because it's all, I'm just copying it straight from the lecture notes. That's basically what I have right here. And so if you just want to sit around, because I know it's a lot of numbers and stuff to keep track of. So if you just want to kind of follow along and kind of just reference either the lecture notes or this video later, I think that's probably the better thing than trying to kind of remember or trying to write down everything in real time. Okay, so that's the contributions from element A. And so for the contributions from element B, I'm going to write in red. Okay, so we have plus 12, plus 6L, minus 12, 6L, okay, plus 6L, plus 4L squared, minus 6L, 2L squared, minus 12, minus 6L, 12, minus 6L, 6L, 2L squared, minus 6L, and 4L squared. So let's box this guy. Okay. And so there's our element stiffness matrix, okay? And so let's write the degrees of freedom out here. So we have U1y, theta 1, U2y, theta 2, U3y, and theta 3, okay? So there's our 6 by 6 system, okay? And so you can see a lot of these guys are going to cancel out, right? And so at this point, you know, before we can solve, we're going to apply boundary conditions, both Neumann and Drishlay. Okay. Okay. And so from the problem, we know that we had a fixed condition at node 1. Okay. Okay. And so the fixed condition at node 1 basically knocks out both the degrees of freedom there. So this means that U1y is equal to theta 1 is equal to 0. Okay. And then we also had a pin. We also have a pin at node 3. Okay. And so this will knock out the translational degree of freedom. So this means that U3y is equal to 0. Okay. And so what this means is that the rows in the matrix that we're going to modify are going to be this one and this one. Okay. Because those two rows correspond to the degrees of freedom U1y and theta 1, because those are on the same rows. And then the other one is going to be this one right here. Okay. And so we're going to replace those rows with our 0, 0, 0, 0, 1s or 1, 0, 0, 0. So our row of zeros with the 1 on the diagonal. And then put the corresponding 0 on the right-hand side. Okay. And then we also have a Neumann conditions, 2 of them, on node 2. Okay. Okay. And so we have a downward force of P. Okay. And so the row that we're going to put this in is on U2y, right? And we also have a moment, I think we called it M. Okay. And this is going to be on the row of theta 2. Okay. And so we're going to modify the forcing vector according to these, in the rows according to the forcing. Okay. All right, any questions on this before I apply all these conditions? Okay. So we'll see if I can write a little bit smaller and fit it all in one row, but no guarantees. Okay, so let's go ahead and fill in everything. So we have EI all over L cubed. Okay. And so our first row is replaced with our Dirichlet boundary conditions. So that's going to be 1, 0, 0, 0, 0, 0. 1, 2, 3, 4, 5, 6. Yep. And our second row is also going to be replaced just like that. Okay. And so from here, we need to start filling in our values from before. So we have minus 12, minus 6L, 24, 0, minus 12, 6L, okay? 6L, 2L squared, 0, 8L squared, minus 6L, 2L squared, okay? And then we have, then our next row is going to be our boundary conditions. So we're going to have row of all zeros except for 1, okay? And then finally, we have the final row, which is 0, 0, 6L, 2L squared, minus 6L, 4L squared, okay? This multiplies by our degrees of freedom. So we have U1y, theta 1, U2y, theta 2, U3y, and theta 3, okay? And this finally equals to our forcing vector, which is 0, 0. We go to our row of U2y. And so remember, we had a force of minus P on that guy. And on the theta 2 row, we have M, okay? And then we have 0, 0, okay? All right, and so that's our final global system. So that's basically as far as we can take this problem. So, you know, normally if you had numbers for these, you can plug them in and you can solve them in MATLAB. But you can see, you know, the basic process of our finite element problems are still the same. For the beams, it's just that, you know, we have an extra degree of freedom and slightly bigger systems to worry about. But, you know, the fundamentals and everything and the process that we went over is still the same. Okay. All right, are there any final questions on this? Okay, so that's all we got time for. So thank you everyone for tuning in. So it's the end of the week, so I posted a new minute paper on the Canvas site. So if you could fill that out, that would be really helpful for me. But again, those are totally optional and they're totally anonymous. So you know, fill them out if you want, but they do help a lot. But if not, then I hope everyone has a great weekend, and I'll see you guys on Monday. So the question is, up to today's lecture is covered on the homework that is due this upcoming Monday. So there's no beam stuff on the homework, but there is truss stuff. So the basically the first part of the lecture today, you need that for the homework that's due Monday. But on the beam stuff, that's going to be on the next homework assignment. Yeah.
Excuse me, Professor, I have a question.
Sure, what's up?
About the beam part. So when you were like writing the global matrix, I guess, based on the differential equations that you wrote there.
Yeah.
So you had like three differential equations, right?
Yep.
But then when we were writing this stiffness matrix, it's by a 4x4 matrix.
Yeah. Right.
How do you get like 4 equations from 3 differential equations?
Right. So actually, you know, the only equations that we actually use to produce that matrix is actually these two right here. And so these two are the force and moment equations, but we actually apply them twice. So basically, remember, our beam element has 2 nodes, right? And so we're going to apply this guy, which is the force is equal to EI d cubed uy dx cubed. And so that provides us 2 equations for our matrix. So we're going to apply this at node 1, and we're going to apply this one at node 2. And so that gives us 2 equations. And then we apply this one, the M equation, twice as well. And we're going to apply that at node 1 and node 2. And so this equation up here, this EI d to the 4th, this is kind of like the starter equation. And then by applying some beam theory, we can manipulate it in order to get these 2 equations down here. And so the first equation is kind of like the starting point, and then from that we spawn these 2 equations in red. And then the equations in red are actually what we use to create the 4 equations for our stiffness matrix.
I see. Thank you. And another thing, so it's like the differential equations is relating the moment to the displacements, or the force to displacement.
Yeah.
But we have theta in our equations too. So like moment is related to theta somehow in the matrix that you're writing.
Yep.
So how is it coming out of those 2 equations? I mean, we don't have any theta in those equations.
Right, so we don't have theta, but if we assume that the rotations are small enough, we can relate the thetas to the displacements using the equation that I've circled in purple right there.
So for like 2 of the equations, we just like, instead of displacement, we replace it with theta.
Exactly.
Got it.
Yeah.
Yeah. Okay, thank you so much.
Yeah, no problem. All right, any other questions? Shear moment diagrams, yeah. So if you look in the textbook, they do shear moment diagrams as well, but that goes a little bit too much into strength of material. So I just want to focus on just the finite element parts. And so we're kind of breezing over these sections. So normally, you would take more time for this, but I just want to get kind of the essentials for finite elements just from these, just so that we can do kind of the stuff after the midterm with like strong form, weak form, and all that stuff. So we're skipping a lot of the strength of material stuff, but that's mostly just so we can focus on the finite element. All right. So if you guys have any more questions, you can always email me. So I'll try to get back to you as fast as I can. But if not, I'll see everyone on Monday. So have a great weekend, everybody.